Imagine the universe in its infancy, a mere fraction of a second old, a time when everything we know was compressed into an incredibly small, hot and dense state. It's a chaotic, energetic soup of fundamental particles, colliding and interacting in ways that would eventually give rise to the matter we see around us. A far cry from the structured cosmos we observe today, with its galaxies, stars, and planets. Yet within this chaotic beginning lies the story of our cosmic origins, a narrative written in the language of physics and chemistry. The formation of the lightest elements like hydrogen and helium stands as a testament to these early moments, providing clues about the universe's initial conditions. A faint echo of creation imprinted on the cosmos, known as the cosmic microwave background, offers a snapshot of the universe when it was just 380,000 years old. By deciphering the conditions under which these elements formed, we can rewind the cosmic clock, piecing together the events that led to the universe we inhabit. Glimpsing back to the universe's infancy and understanding the processes that shape the universe we see today, we uncover the secrets of cosmic evolution. One of the keys to unlocking this cosmic history lies in understanding the formation of deuterium, a crucial isotope in the early universe. Deuterium, often called heavy hydrogen, is an isotope of hydrogen containing one proton and one neutron in its nucleus, playing a vital role in the universe's development. Its formation marks a pivotal stage in the early universe, a stepping stone to the creation of heavier elements like helium and beyond, a stepping stone to the creation of heavier elements like helium, which would eventually lead to the formation of stars and galaxies. By studying deuterium, we gain insights into the universe's age, temperature, and the balance of matter and energy during its formative moments, helping us understand the grand tapestry of cosmic history. In the universe's first fleeting moments, temperatures were unimaginably high. Protons and neutrons, the building blocks of atomic nuclei, zipped around at incredible speeds, colliding with tremendous energy. Yet the formation of deuterium, a seemingly simple union of a proton and a neutron, faced a significant hurdle: the overwhelming abundance of photons, the particles that make up light. This is where the nucleon-to-photon ratio comes into play. This ratio, denoted as ETA, represents the relative abundance of protons and neutrons, collectively called nucleons, compared to photons. In the early universe, ETA was incredibly small, around 10 to the power of -10. This means that for every proton or neutron, there were billions of photons. These photons, constantly colliding with protons and neutrons, possessed enough energy to blast apart any newly formed deuterium nuclei before they could settle into a stable existence. As the universe expanded, it cooled. This cooling played a crucial role in the eventual formation of deuterium. To understand this connection, imagine the early universe as a cooling oven. Initially, the intense heat representing high photon energy prevented any lasting bonds between protons and neutrons. As the oven cooled, the energy of the photons decreased. Eventually, the universe reached a temperature where the photons no longer carried enough energy to break apart deuterium nuclei. This critical temperature, around 1 billion degrees Celsius, marked the beginning of deuterium formation. Using cosmological equations that relate the universe's temperature to its age, we can pinpoint the time when this pivotal event occurred, approximately 1 minute after the Big Bang. This period, known as Big Bang nucleosynthesis, BBN, is when the lightest elements, including deuterium, helium, and lithium, were forged. The formation of deuterium wasn't just about overcoming the disruptive energy of photons. Another crucial factor was the delicate balance between protons and neutrons. In the very early universe, neutrons and protons existed in near equal numbers. However, neutrons are inherently unstable particles, prone to decaying into a proton, an electron, and an antineutrino. This decay process had a significant impact on the eventual abundance of helium in the universe. As neutrons decayed, the initial balance tipped in favor of protons. This shift had significant implications for deuterium. Since deuterium formation requires one of each particle, the decreasing number of neutrons limited how much deuterium could form. The lower the neutron-to-proton ratio, the less deuterium could be produced, before all available neutrons were locked up in heavier nuclei. The neutron decay process, while seemingly detrimental to deuterium formation, provides a valuable tool for cosmologists, a cosmic clock. The half-life of a neutron, the time it takes for half of a given sample to decay, is approximately 10 minutes. This relatively short time frame, coupled with our understanding of nuclear physics, allows us to calculate the neutron-to-proton ratio at the time of BBN. By knowing the initial neutron-to-proton ratio and the neutron's decay rate, we can calculate how long neutrons had been decaying before they were incorporated into deuterium and subsequently helium. This calculation provides a crucial independent measure of the universe's age during BBN, corroborating the estimate derived from the universe's temperature. Section 6. From protons to helium, forging the lightest elements. With deuterium formed, the stage was set for the creation of helium-4, the most common isotope of helium. This process was a crucial step in the early universe, laying the groundwork for the formation of heavier elements that would come later. Two main reactions dominated this process, each playing a significant role in the synthesis of helium-4. The first reaction involves deuterium plus deuterium, which yields helium-3 and a neutron. In this reaction, two deuterium nuclei collide, producing a helium-3 nucleus which consists of two protons and one neutron, and releasing a free neutron. This reaction is fundamental in the chain of events leading to helium-4. The second reaction is helium-3 plus deuterium, which yields helium-4 and a proton. In this reaction, a helium-3 nucleus collides with another deuterium nucleus, forming a stable helium-4 nucleus, which has two protons and two neutrons, and releasing a free proton. This stability is key to the element's abundance in the universe. These reactions highlight the crucial role of deuterium as a stepping stone in the formation of heavier elements. Without deuterium, the synthesis of helium and other elements would not be possible. The released neutrons could then participate in further reactions, contributing to the buildup of helium-4. These neutrons are essential in the ongoing process of nucleosynthesis. The efficiency of these reactions depended on the conditions present during Big Bang nucleosynthesis, particularly the density of baryons, which are protons and neutrons, and the previously mentioned neutron-to-proton ratio. These conditions were critical in determining the abundance of elements. By studying the abundance of light elements like helium-4, we gain further insights into these early conditions and the processes that governed the universe's evolution. This knowledge helps us understand the fundamental forces at play in the cosmos. Section 7. The helium-to-proton ratio, a cosmic fingerprint. The final abundance of helium-4 relative to hydrogen, known as the helium-to-proton ratio, provides a crucial test for our models of the early universe. This ratio, primarily determined by the neutron-to-proton ratio at the time of Big Bang nucleosynthesis, can be predicted with remarkable precision using our knowledge of nuclear physics and the conditions present during this early epoch. Observations of the cosmic microwave background radiation, the afterglow of the Big Bang, and the abundance of light elements in distant primordial gas clouds all point to a helium-to-proton ratio of roughly 1 to 12. This remarkable agreement between theoretical predictions and observational data provides strong support for the Big Bang theory and our understanding of the processes that shaped the universe's first few minutes. Section 8. A universe in its infancy, the significance of early helium abundance. The formation of helium-4 during Big Bang nucleosynthesis had profound implications for the evolution of the universe. Helium, being chemically inert, played a crucial role in the formation of the first stars and galaxies. The abundance of helium influenced the cooling and collapse of primordial gas clouds, ultimately affecting the rate and characteristics of star formation in the early universe. Moreover, the precise abundance of helium-4 serves as a sensitive probe of fundamental physics. It provides constraints on the number of neutrino species, the strength of the weak nuclear force, and even the existence of exotic particles beyond the standard model of particle physics. By studying the cosmic abundance of this light element, we delve into the heart of particle physics and cosmology, probing the fundamental building blocks and forces governing our universe. Section 9. Our cosmic origins. Looking back to the dawn of time. The journey from a hot, dense soup of particles to the formation of the lightest element stands as a testament to the power of physics to unravel the universe's history. This transformation, driven by the fundamental forces, laid the groundwork for everything we see today. By studying the formation of deuterium and helium, We peer back to the universe's infancy, a time when temperatures were unimaginable and the fundamental forces of nature were just beginning to shape the cosmos. These early moments were crucial in setting the stage for the complex structures that would eventually emerge. The remarkable agreement between theoretical predictions and observations of light element abundances provides strong evidence for the Big Bang theory and our understanding of the universe's early evolution. This harmony between theory and observation is a cornerstone of modern cosmology. Furthermore, the study of these primordial elements continues to push the boundaries of our understanding, offering insights into particle physics, cosmology, and the intricate interplay of fundamental forces that govern the universe's birth and evolution. Each discovery brings us closer to comprehending the vast tapestry of the cosmos. As we delve deeper into the cosmos, we uncover not only the story of the universe's past but also clues to its future, ultimately seeking to answer the most profound question of all: how did it all begin? This quest drives our exploration and fuels our curiosity about the universe's ultimate fate.